gained from the Department of Statistics and Biostatistics of Rutgers to speak about partitions and random partitions.
Thanks, Doron, for the invitation. Yeah, so as you mentioned, I'm going to talk about random partitions and random permutations. So I come from the statistics department, and a lot of the work I do involves some kind of probability on discrete spaces. So I'm going to survey some work in the area of random partitions and random permutations. So these come up in various different applications. I won't focus too much on those. But the distributions that I'll talk about, I think, are interesting in their own right, and there might be potential. I suspect there's a lot of potential for some crossover between interesting problems that people here might be interested in who work in enumerative combinatorics and answering similar questions about these probability distributions, these more general distributions on these spaces. And there's also plenty of opportunity, I think, for using computers to simulate these random partitions and permutations and to answer interesting questions in that way. So I'll break the talk up into two parts. The first part I'll talk about partitions. So I should say that when I say the word partition, I mean set partition. Partition of a set. I know there's been a lot of talks in this semester about integer partitions, and I won't. When I mean partition of an integer, I'll say integer partition specifically. Okay. And so in this case, I'm interested in partitions with a special property called exchangeability that I'll explain in just a bit. And the family of Ewan's random partitions, so it's called the Ewan's process, is a family of probability distributions on set partitions from about 40 years ago. This was discovered by Warren Ewans in the literature on theoretical population genetics. So in that context, some partitions came about. But the distribution that I'll talk about here, this has some very nice properties that I'll discuss. And then in the second part, I'll talk about random permutations. And I'm going to use the word ranking to interchangeably with permutation, but I use that specifically because I'm going to think about a permutation as a linear ordering of a finite set. And I'll use permutation to mean a bijective function because I'll use them both in this talk. And so I'll be interested in rankings with a special property, and in this case, the family of distributions I talk about is called the Mallows process. So this is Colin Mallows, who I'm sure some of you here know.
Yes.
And this was work from quite a while ago, and he was working on some problems in statistical problems on ranking data. Okay. So these are the two. This is the main. This is what I'll split the talk up into these two parts. If there are any questions, please let me know. So first, I want to get some notation before we proceed. So a partition is going to be a collection of non-empty disjoint subsets. I'll use the notation lowercase pi to denote a partition. These are the blocks of the partition, so these are non-empty. They're disjoint. And their union is some set of the first n positive integers. Okay, and I'll use the notation script p to be the set of all partitions of a given finite set. So I know where I am. These are enumerated by the Bell numbers. And so, for example, the
order doesn't matter.
The order doesn't matter, no.
Yeah, so the
order of the blocks doesn't matter.
Yeah, so the B1, BK should be a set, really. It's a set of B1.
B1 is a set?
Yeah, but right now it's order, so this is order. So
I write them, okay, so the convention I use is that I'm going to list them in increasing order of their minimum element, so I'll make that clear in a minute. So when n is equal to 3, there are 5 partitions as we see here, and so I'm listing the blocks in increasing order of their smallest elements. So I'm not going to separate them by commas or anything like that. This is the trivial block, trivial partition with 1 block. Here we have 2 blocks, and here we have 3 blocks. And
Stirling numbers of the second kind.
Right, for when we count the blocks, when we consider the blocks. Right. So sometimes and later in the talk, it'll be convenient to represent a partition by its restricted growth function. So the restricted growth function is just a string of length n. So for a partition of a set of size n, the restricted growth function is a string of length n where rho I is the index of the block containing element I. And this is when I write the blocks in canonical order, in increasing order. So for example, let's say I have this partition here. So I've written the blocks in increasing order of their smallest element, and this corresponds to, well, the first element always appears, the element 1 always appears in the first block, and then here the next 2 appear in the second block, then the 4th is in the first, 3rd, and so on. Okay. So that'll come up later in the talk. But what I'll be talking about mostly is this family of distributions called the Ewan's distribution, and I want to put it here so it's up the whole time. Ewan's distribution takes a parameter alpha, so it's a positive number, and it assigns a probability. So we think of having a set of all partitions of some finite set of size n. So I'll use capital pi to mean that I'm talking about a random partition, and the probability that this random draw takes a specific value pi is going to have this form. So there's some part that we have alpha, the parameter raised to the power of this is the number of blocks in pi. This is the rising factorial, and then we have the product over the blocks of this factorial of the size of the block, the cardinality, minus 1 factorial. So number pi, this is the number of blocks. And this is the rising factorial. And this distribution, it may not look like it, but it has some nice properties that originally, as I said, it came up in population genetics, but I've actually seen it come up in many other contexts, in number theory, linear algebra, and now it's used widely in statistics. So there's quite a bit of interest in this family of distributions. Okay.
Is it obvious that it adds up to 1?
It's not entirely obvious. No, it depends how you derive it. But I'll show a way to derive this later that it will be obvious at that point. Okay. And so in the second part, I'll talk about permutations or rankings. So I'm going to write a ranking now as also denote this by rho, so it's going to be a string of length n. But now this is just going to be a linear order of the set of the first n positive integers. Okay, so I'll use Sn, the usual notation, Sn to denote the set of the first n rankings of the set of size n. So these, of course, are in one-to-one correspondence with permutations. So they're enumerated by the factorial numbers. And so in the easy case, when n is equal to 3, there are six permutations. And these grow quite rapidly. And so we'll be interested in putting a probability distribution on this set. Of course, in any situation when you have a finite set, you can always just put the uniform distribution. But there's reasons why that's not natural in certain applications. And so in this setting, in the partition setting, we define the probability distribution in terms of some statistic or some function of the partition. So we see that the probability depends on the number of blocks and also the block sizes. And in the case of permutations, we're going to be interested in how disorganized the ranking is. So we're interested in the number of inversions. So an inversion in row in the ranking is a pair for which I is less than j and row I is bigger than row j. So that means just that the elements that appear in positions I and j are in the wrong order, if we think about the right order being that they're listed in increasing order. So the statistic that we'll be interested in for rankings will be the number of inversions. So the number of inversions here is 0, since this is just in increasing order. There's one inversion here given by 3 and 2, one inversion here, 2 inversions given by 2 and 1 and 3, 1, and so on. And so what the Mallows distribution does is it assigns a weight to each ranking according to how many inversions it has. So there's some parameter q in this distribution, and the probability assigned to a random ranking of a set of size n is q raised to the power of the number of inversions divided by the inversion polynomial. So this is the generating function for the number of inversions of a set of size n, and it has a nice product form. And here's my homework here. That's given by a triangle, so for each n we have a triangle of these inversion numbers. Okay, so these are the basic ingredients of the talk, and I'm going to start by talking about the first part, which is random partitions.
So they're the Eulerian numbers, right? That triangle of numbers.
Oh, okay. Is that what they're called?
Many of them, maybe one.
Okay, so I'm interested in certain families of random partitions, particularly exchangeable partitions, and this is a common thread in when we study probability distributions on partitions, but I also think it's natural in combinatorics as well. That we're only really interested in the structure of the set partition. We're not interested so much in the elements that appear in each of the blocks. So we're interested, if you will, in the isomorphism classes of the partition. And so that naturally, there's a natural relabeling operation that we consider that we want the distribution to be invariant under. So we define the relabeling So if we have a partition of n elements, we can relabel it by a permutation. And now I'm regarding a permutation as a bijective function. Is given by, I'll write it as pi superscript sigma, which I define by saying that I and j are going to be in the same block of the relabeled partition. So this is just the equivalence relation induced by the partition, if and only if their inverse image under the permutation is in the same block of the original partition. So the definition is actually pretty clear once we do a simple example. So if we take the same partition that we dealt with down here, and take the permutation, for example, this one, which will send 1 to 2, 2 to 3, 3 to 1, and so on. Then the relabeling we obtain by just mapping each of the elements under sigma. So if we just do, so 1 maps to 2, 4 goes to 5, 6 and 7 are fixed, 2 goes to 3, and 3 goes to 1, 8 is fixed, and 5 goes to 4. So when we write this in canonical order, we get this. And so notice, and this will be important, notice that the block sizes don't change. The number of blocks doesn't change under relabeling, and also the block sizes doesn't change. There's a block of size 4, a block of size 3, and a block of size 1, and there's one of size 4, 3, and 1 here, and the order doesn't matter. And so I'm interested in distributions, random partitions whose distribution is invariant under this relabeling operation. That's what I define to be an exchangeable random partition. So my random partition pi sub n, so capital Pi means it's random. I call it exchangeable if the probability that I take any value, so the probability that I realize any realization is some partition is equal to any relabeling of that same partition. This is for any permutation and for any partition pi. Okay. So an obvious example of this is the uniform distribution. So if we consider partitions of the set of 3 elements, there's 5 of them. And so the uniform distribution...
So that's a general definition for an arbitrary distribution.
Yes.
And here, this is a specific.
This is a specific example.
So,
yeah.
So you use pi n in different contexts.
Well, pi n is just a random... So I'm not saying that this necessarily corresponds to that.
Yeah, it's different.
Right, yeah. So this is just a general probability measure on it for a general random. So under the uniform distribution, we assume we just have a set or a box with all of these partitions in it, and we pick one out with each having equal probability. So the probability under this distribution, this assigns equal probability 1/5. And so if in any kind of enumerative problem in combinatorics can be rephrased in terms of a probabilistic problem using the uniform distribution. So there's a trivial correspondence there. And what I'm going to talk about today is that, well, what I want to convince you of is that this is not always a natural thing to consider. So there's reasons why we want to consider distributions that aren't uniform. And that has to do with statistical properties dealing with subsampling. So in a statistical context, we think of having a large population and we sample from it. We can only observe a little bit of information about a large population. So if we think of having a partition of a large set, we can only observe a small, a restriction or a part of that partition. But we want to use what we observe to get information about the whole population. And we can only do this if the distributions that we assume somehow are compatible with one another. There's some mutual coherence between these probability distributions. And so so in this context, the idea of subsampling, when we take a subsample from a set, that induces a restricted or a reduced partition, which is just the definition you probably would assume it to be if you have seen it before, but the restriction of a partition pi to a partition of n elements. So pi is a partition of n elements. I'm assuming that I want to restrict it to some smaller set of m elements is given by the partition we would obtain if we just remove. So we just have to remove any elements that are not in the set M. And also we remove any empty sets that result from that. For example, in this case, the restriction of this partition to set of size 4 we get by just removing any element that's larger than 4. And so now we want to specify a family of probability distributions. So one for each n, so the sample can be of any finite size. We want a family of probability distributions that is somehow consistent with respect to this restriction operation. And so that's what I'll call compatibility. So I call a family pi n. So here I have a random partition for each finite set. It's called compatible if the distribution induced, so if the induced distributions line up with the marginal distributions, so what that means is if I take a partition of size n and then I restrict to partitions of m, then that's going to give me a random partition of m elements, and I need that random partition to have the same distribution as pi sub m. So by definition, I have a partition of n elements restricted to m elements. The probability that I observe pi, so pi is now a partition of m. This by definition is obtained just by summing over all of the partitions that agree under restriction. So now I'm taking a sum over partitions of n whose restriction to m is equal to pi. And I have to sum all of the probabilities of pi n. And these are consistent if and only if this is exactly equal to the probability distribution for the partition pi n. This is for all n less than. Okay. So to illustrate what that means, consider the example I have up here for the uniform partition. So these two partitions under restriction to two elements will just restrict to 1, 2, and these three will restrict down to the block or the partition with 2 blocks. And so if we sum these probabilities, we get 2/5 and 3/5. And so, in particular, the family of uniform distributions is not compatible, and so it wouldn't really, it doesn't quite work for what we typically want. Okay?
It should have been a half and a half.
It should have been yeah. So if it were compatible, then these would be a half and a half. And so this is different. And this will be different in general if we went up for any n. I mean, it might work out somewhere, but I highly doubt it. Okay, so the point now is to say, well, the distribution up there, the Ewens distribution, satisfies both of these properties. So it's exchangeable and it has this compatibility property. And the compatibility property, I should say, is what makes this very convenient for computer simulation, because it allows us to build the distributions, build a sequence very quickly, because we can build these up recursively using the same source of randomness. And you can't do that for uniform partitions.
And is the Ewens one the only one that has both properties?
No, it's not. No, there's a whole family of them that do, but this is the only one that's really nice enough to write down in closed form. Yeah. So, assuming that pi n is a Ewens partition, this just means that pi n has the Ewens distribution for each n. Then the family of this family is both exchangeable and compatible. Okay, so first to establish exchangeability, all we need to do is really look at this. So I made an observation here that when we relabel a partition, we don't change, the number of blocks won't change, and the block sizes won't change, and the distribution in the Ewens distribution only depends on the number of blocks and the block sizes, so it'll be invariant under relabeling, so it will be exchangeable. The interesting part is the compatibility. So, and a way to show this. So there's a nice and an easy way to show this using induction, and it's through something called the Chinese restaurant process. So this is a construction due to Jim Pittman. So I should say that nothing that I'm talking about is my work. So I wanted to take the opportunity to introduce these ideas and survey some of them. So this is due to Jim Pittman, where we can generate the sequence, this sequence pi n recursively by building it up and inserting elements one at a time. And so we associate the blocks of the partition with tables at a restaurant, I suppose. So there's an unlimited number of tables, and so each table corresponds to the blocks, and so after customers arrive, they're seated at these tables, and so in this case, this corresponds to generating this partition of 5 elements, and then when the 6th element arrives, it's going to be placed into these blocks according to some probability, some conditional distribution. So it'll either be placed in this block, or it'll be placed alone as a singlet. So those are the only 3 possibilities. And so the way that this works is that I take the n plus first element and I insert it into some block B, conditional on the configuration of n elements. Preferentially, I'm going to put it into blocks that are already large. So if the block is occupied, so if there's already elements in the block, then I place it with probability proportional to the current cardinality of the block B. So in this case, the 6th element will be placed in the first block with probability 3 over 5 plus alpha, and this block 2 over 5 plus alpha.